So, around the 80s of the last century, several authors studied the global existence of small data solution for these two kind of semilinear wave equations. And I only sit here, John, Cato, and Kleinerman, but there are others authors. And our question here is what about the influence of variable coefficients on their results? So let us discuss about the global existence of small data solution to the Cauchy problem for the dissipative nonlinear wave equation 1.1. So we added this dissipative term, and for us here, phi and psi will be in the space of the infinite function with compact support. I only will write down this equation here, minus 8t squared 2xx, a gradient. Okay. So then I will put some previous results. The first model is the case where A is identically 1. And for this model, you have global existence of small data solution. The second model is a similar one with this. You don't have global existence of small data solution, at least for one space dimension. And you can get this by applying the functional method. This is a well-known method. The third model is got by Adjan, 2001. It is in the case that the function A is a non-negative, one periodic, positive coefficient. You can take, for example, A as some perturbation of the case A identically 1. And in this case, you don't have the property of global existence of small data solution. So this result shows that oscillation on the coefficients in general have a deteriorating influence on the global existence of small data solution. The next model is done by Wirth, 2003, is the case that the function A is a polynomial growth. And in this case, we have the global existence of small data solution. So this example shows that the strictly increasing coefficient may have an improvement on the influence of the global existence of small data solution. The other model is by Wirth again. It is in the case that the coefficient A have some decreasing to 0 when t goes to infinite. And in this case, you don't have the global existence of small data solution. So this example shows that the strictly decreasing coefficient tends to 0, may have a deteriorating influence on the global existence of small data solution. So one can ask, in the case of the function A, goes like decreasing but to a constant, for example, what happens in this case? This was a question proposed by Colombini in 2006. Indeed, it was a question related to Strichard estimate, and then 1 year later, Hirozawa, introduced the notion of stabilization property in order to answer these questions. And we can apply this in order to have a positive result for the global existence, even in this case. So this is not a problem, decreasing. The problem is if A decreasing to 0, then you have a problem. If not, you can still have a positive result. So our model of interest will be the case we will split the function A indeed in two parts with a function lambda times bt. So this lambda will be a shape function, and the b will have some oscillation. So lambda describes the asymptotic behavior, and the b will include some oscillations that you know that you cannot have arbitrary oscillation, so you need to have some control in this oscillation. And the dissipative term we will assume to be non-effective. We call this non-effective in order that you have several results about the effective dissipation that are related to the diffusion phenomena that have some relation between the wave equation and the parabolic equation. They associate parabolic equation, and then it seems to be that the problem is easier to deal with. So the case of non-effective seems to be more critical. So I will explain later what means this non-effective. So question, can we understand the interplay between the coefficients in order to prove global existence or in order to show that you cannot have global existence? So the answer is yes, we can. So in the case C identically 0, there are results of Wirth, 2003, and Yadjian, 2005, for higher dimension, n greater than or equal to. In the case n equal 1 was considered by myself and Reisig, 2011. Seems to be more difficult the case one dimension space. So the assumption now will be lambda and b C2 positive. So you are strictly hyperbolic, Cauchy problem equation, and the function C is the class C1, our real value, and we can assume lambda and 0 equal 1 positive, and for the function B that are bounded, the function B. There are some oscillations, but bounded. Okay? So the first hypothesis, we define capital lambda is the primitive of lambda. You will assume lambda not in L1. Okay? And in order to control the behavior of the coefficients, we need to assume 2.3. The condition on lambda, the eta, the function eta here is lambda over capital lambda. So the estimate for lambda, we call this in something a shape function. Okay. And the estimate for b here is, you see, we need to have some decay that can depend on lambda. The function b can oscillate, but need to have some decay that depend on lambda. And this condition on C means that we call non-effective. For now, we call this non-effective, this estimate that C needs to satisfy for the first, C on his first derivative. The second hypothesis now, we take gamma is exponential of minus integral of C, and you assume 2.4. You see that if C is identically 0, we need to have lambda increasing, like in the previous example. We know that you need to assume this kind of hypothesis, okay? But more in general, we need to have this condition. Indeed, you can even have a more general condition here. You assume only lambda over gamma, quasi increasing is sufficient. But for now, we assume increasing. And the hypothesis 3 if gamma over eta is not bounded, we assume 2.5. We have some condition. You see that for one space dimension is a stronger condition that you need to have. For higher dimension is more easy that 2.5 holds here. Okay. Under these three hypotheses, you can set out theorem is under hypothesis 1 to 3 that exists for giving phi and psi in C infinite with compact support function. There exists a unique global in time classical solution of 2.6, the Cauchy problem 2.6. Here, of course, for small data, then for all epsilon between 0 and epsilon star with for suitable epsilon star. So I will give some examples now. Then hypothesis 1 to 3, you can verify for these three examples. For example, if lambda is a polynomial growth, you take L greater than minus 1 in order that are not in L1. Then you can take the dissipative term C like this, but you need this condition, mu greater than minus L. Okay? If lambda is identically 1, you can have this dissipative term for me greater than 1. And if lambda is exponential, a positive p here, then the function C, the dissipative term, can be a constant, but mu greater than minus p. For all this choice of lambda and C, we can take the function b in the equation like this, capital F log 1 plus capital lambda. So this function b, you see capital F here is a periodic function. So you have oscillation, but you need to have some decay. You cannot have an arbitrary oscillation function b here in this equation. Okay. Our open problem here is in the case lambda identically 1 and C like this for mu greater than 0 is smaller than or equal 1. Hypothesis 1 and 2 holds, but hypothesis 3 does not hold for any identically 1. So for now we cannot answer this question. Of course, that you take B like this, with some oscillation. If B is constant, maybe it's more easy to answer this problem, okay? A non-existence result for global solutions, we consider this model 3.7 is a similar model with our here. And for the function f, we assume f in C infinite that vanish in 0 and have these estimates. So the proposition is the following. Suppose that the integral of the function psi is greater than 0, this initial data, and the capital phi given by this integral goes to infinity when t goes to infinity. Then the solution u of 3.7 blows up in finite time. Okay? This is a well-known result. You can just apply this functional method. You consider this functional. And then if you differentiate on t this function j and apply Green formula, Holder inequalities, you arrive this estimate from below for j. And then you can see here this function, if you have even for small data, this will be large, but since if capital phi goes to infinity, this term in some moment, in capital T equal capital T, this goes to 0, and then since this term here is negative, P is greater than equal to, then this blows up in finite time, okay? So in some sense, you can see that this condition 3.9 are exactly these hypothesis 3 that we assume, at least in the case P identically 2. For P equal 2, this is exactly the condition that we assume in hypothesis 3 to be finite. Okay? How many time? 5 minutes. I will try only to give an idea of the proof. So the first step is to apply Nirenberg transformations. Then you can reduce to a linear problem under some condition. And then for the linear problem, we need to obtain some uniformity estimate for the partial Fourier transform with respect to x, to the solution of the linear equation. And finally, apply this L1, L infinite estimate. Okay? So the Nirenberg transformation is given by this one. So you can rewrite our problem to 4.10, a linear problem, under this constraint condition, if V is less than 1. If you have this constraint condition, you can have a linear problem. So what you need to have to prove this condition? V, Tx uniformly estimate by 1. So the uniformly estimate, so you apply the Fourier transform in X to this Cauchy problem. And now you need to divide the fuzzy space in two zones. Basically, it's easy to see here in the step 2. You divide the space fuzz in two zones here. These we call hyperbolic zones, and this pseudo differential zone. And here is this function, theta, that divide the fuzzy space. And then you can have these two estimates. In the hyperbolic zones, we have these estimates uniformly on T and psi. Indeed, this 4.12 is a two-side estimate. You can get an estimate from below. And in the pseudo-differential zones, we have another estimate here. So if you put together this, one more lemma is, if the hypothesis 3 holds, then this integral is finite, is bounded. Okay, this you need to assume. And then we only to apply these L1, L infinite estimates is easy. This is always holds that you can estimate the L infinite normal function by the L1 of his Fourier transform. And then if gamma over eta is not bounded, you have this estimate. And by using the 4.13 here is the estimate in the pseudo-differential zone. So if you apply this, you see you only all the time apply this estimate. So since by hypothesis 3 this is finite, then you have this estimate uniformly. And since the data are in say infinite function with compact support, this is finite. You can take even small. And the same for the hyperbolic zone. You can get this estimate. And this is usual, denote the pseudo-differential operator with this symbol. And again, if the data are in C infinite with compact support, this is finite. For small data, is small. So you can get that the L infinite norm of the function V is smaller than 1, and then you have the global existence result. You have some reference, and thank you for your attention.